Hey everyone, Mr. Newman here. Today we're going to do numerical definite integrals, and it's going to build on what we learned before. So the real question is, how do we evaluate the area of a function that's not made up of geometric shapes like we had before? And we had a glimpse of that, an idea with the Desmos activity. If you didn't get to do that from class or didn't see that, please go back there and try that. But the basic idea is, with any curve, you can approximate the area under it with these rectangles or with trapezoids. Okay, we didn't get to see trapezoids there, but we will here. So those are the two numeric methods. All right, there's Riemann sum, and there's the trapezoid rule, which is using trapezoids. All right, and within the Riemann sums, we have a left sum, a right sum, and a midpoint sum, which the midpoint, as we saw, is the best of all the Riemann methods. We'll see a little bit more of that today. And then the trapezoid actually is the best of all the numeric methods, so it's even better than the midpoint, okay? So the way the Riemann sum works, as you all saw, is it's approximations of the area using rectangles. And of course, as you can guess, the trapezoid rule uses trapezoids. So one of the things that hopefully you saw was the width of that rectangle. If you have, let's say, an integral here, and we're dealing with an area from a to b of f of x dx. Remember, that's the area under the curve from a to b, and that width of the entire thing is going to be b minus a, right? But we have this number n. N is the number of rectangles that we're using to count. So if we take that entire width, divide by n, then you get the width of each individual rectangle. And so we have a few formulas. I'm going to write two formulas here that you can use. One is if we just take the function value, that's f of x, and we multiply that by the width, and we do that for each rectangle, right? So I'm using x sub 1 for the first x value, x sub 2 for the second x value, and then each width would be separate here, right? F of x sub 3, w3, and so on. But we can actually simplify that if all the widths are the same. They aren't always, but a lot of the times the widths are the same. So we can factor out, suppose all those w's were the same. In fact, suppose that they were right here, suppose they were this b minus a over n. We can factor that out to the front here and just write down b minus a over n, and we can multiply that by what's left over. So the first x value, f of the second x value, and so on all the way to f of the last x value, okay? And those are just the y values. Of course, these values depend on whether you're talking about a left, a right, or a midpoint sum, because that's going to change slightly which x values you plug in to get those y values. For the other one here, the trapezoid rule, I just want to remind you the formula for the area of a trapezoid is you average out the two bases, so base 1 plus base 2 divided by 2, and you multiply that by the height. So again, you could do that over and over and over, and I could write this out where you write that down over and over. But a neat thing happens is that you can actually factor out some of this, and we're going to look at this in a little bit here towards the end of the video, to where you get this formula, b minus a over 2n, it's 2n there, and then it's actually the first x value, that's f of a in our integral here, right, f of a, plus 2 times all the middle ones, so 2 times f of x sub 1, 2 times f of x sub 2, so all the ones between a and b, all the way until you actually don't multiply the last one by 2. Okay, and we'll look at how to do that in a little bit later too. So let's do some practice problems. As always, the things that are inside the rectangles here, you want to memorize this, okay? So I'm going to write down memorize. If you use flashcards, please do that. All right, that will help you out with this this class. All right. So first of all, we have a function, and we're going from 1 to 4. So let's write this as a definite integral. So we write integral with lower bound 1, upper bound 4 of 1 over x dx. Okay. And we're going to find an approximation for the area using 3 rectangles. So as you can see, we're going from 1 to 4. So it divides up nicely. We have 1 rectangle, 2 rectangles, 3 rectangles that we'll be able to use for the base. So first one we're going to do is we're going to do left endpoint. So for that, I'm going to use my first value, and I'm going to select that, and I'm going to make the point there, and then the second value. And the third value, I'm not going to use the last value here because the last value is not the left side of any rectangle, right? And I have this handy dandy shapes tool. I'm going to draw my shapes using the rectangles that come from that. They're all approximations. There we go. And there we go. So you see I have my 3 rectangles. And let's calculate the area here. So we have the area. Notice all the widths are 1. So I can factor out a 1 and just multiply it by each of the heights. Okay, so I factored out a 1, though I could just multiply them just the same, right? And the height, so this is going to be f of 1 plus f of 2 plus f of 3, right? Those are the 3 heights. F of 1 is there, f of 2 is that height, and f of 3 is that height. Well, what is f of 1, f of 2, f of 3? Our function's 1 over x, so we end up getting 1 over 1 plus 1 over 2 plus 1 over 3. And when you type that out, you get 11/6, or I'll just approximate it. You get about 1.833. And yeah, so that's using the left endpoints. And so the question is it an over or an under approximation of the area under the curve? So if this is the area under the curve, then do my rectangles, do those over approximate or under approximate? And hopefully you see here, because of this excess on top of the rectangles there, it is an over approximation. And so the reason for that is actually because because f of x is decreasing here. Okay, so it has to do with it being f(x) decreasing, and it's a left endpoint approximation. Okay, when those two are happening, then you actually always have an over approximation. Let's draw a right endpoint so you see an alternative to that. So for the right endpoint, we're actually not going to draw that first point there because f of 1 is not the right side of any of the rectangles that we care about. So we're going to draw f of 2, f of 3, and f of 4. And let's now make the rectangles based on that. So there's one rectangle, there's another rectangle, and there's another rectangle. So again, our width is always 1, right? So I'm going to factor out the 1. And what's left? We have f of 2 plus f of 3 plus f of 4. Notice here a few things. Notice how all these numbers shifted over. So with left endpoint, we start with the first one, but don't count the last one. And with right endpoint, we count the last one, but don't count the first y value, right? And that's just the nature of which endpoint we're selecting. And remember that for later. So what is f of 2? Well, that's 1/2, right? I was doing all these in purple, whatever. 1/2 plus 1/3 plus 1/4. And if you type that into a calculator, you get approximately 1.083. So you can see it's a lot less than this, and that's good because we see visually these are all smaller, right? So this is going to be an under approximation of the curve, and the reason for that is because, look, there's that space above each of the rectangles that we didn't count. And so on here, I can simply say because f of x is decreasing, and of course it's decreasing on a right endpoint estimation or approximation, right? A sum here. And so notice the fact that it's decreasing isn't enough to say that whether it's over or under, it's decreasing on a left hand sum. And of course, this is an under approximation because it is decreasing on a right hand sum. And of course, if you don't have to memorize that, you can always draw that in picture and just see what's going on there. Okay. For the trapezoid rule, we're actually going to calculate. We're going to find trapezoids here, and see that is the first trapezoid. Okay. So we can't actually just draw that. I'm going to need to calculate it. Sorry, I can't just draw it with my handy dandy tool. I don't think there's a trapezoid tool on Cami here. And so notice I got these points made. I should have made the points more clear. There we go. So you notice this is a much better approximation of that curve. So how do we find these areas of the trapezoid? Well, you take the left. Remember, this is f of 1 and this is f of 2, right? And so on. So f of 1 plus f of 2, those are the two bases. You average them out and you multiply by the base. So the base here is 1, right? And then you add it to the next trapezoid. So you do f of 2 plus f of 3 over 2 plus, times 1. I want to not forget to multiply by the height, even though it's 1 here, so it doesn't change it, but I want to make sure we have that structure in place, over 2 times 1. Okay, and of course this is f of 3 and f of 4. So I want to give a little hint as to, notice if I want to factor this out, I could factor out a 1/2, and look what happens. We have a single f1, and we have two f2s. Let me change the color on this. See, there are two f2s, and then there are two f3s, and then when we get to the very end, there's only one f4 again, okay? And so that comes back up to this, the formula. Notice when we're adding this up, you only have one of the first one and one of the last one, but you have two of all of the other inside y values. This is actually exactly why, because when we factor out this, actually you factor out the width and the dividing by 2, that dividing by 2 goes right here. See that dividing by 2 right there? And of course this is the width of the rectangle. So what's left over is you actually double up on a lot of those, or on all of the interior vertical heights. But let's go ahead and just write this down. So we do get, well, I'll factor out the 1/2 just to speed it up, writing it down a little bit. What do we get? We get f of 1 is 1. We get 2 times 1/2. We get 2 times 1/3. And then we get 1/4 all by itself there, right? So we get 2 times each of the interior, and each of the outside are just 1. When you plug all that in, you end up getting about 1.458. And so you notice it's in between those, so it is a closer approximation. For the midpoint right here, what we need to do is we actually need to, I'm going to zoom in just a smidge here, just a little bit more. We need to find the midpoint first, and so the midpoint of 1 and 2 is going to be 1.5. The midpoint of 2 and 3 is going to be 2.5, and the midpoint of 3 and 4 is going to be 3.5. And those are the values that we're going to use to draw our rectangles, those y values, okay? So let's draw these now. This is kind of eyeball it. There we go. Oops, moved a little at the end. I don't know if I like that. Okay, that was close enough. There we go. So notice a few things actually. The trapezoid rule is a better approximation because it averages the y values. Here, this y value is not necessarily halfway between these two, right? In fact, halfway between those two is going to be above because it's curved down. So the midpoint finds the midpoint first and then finds the y value based on that. Of course, here we would have f of 1.5 times 1 plus f of 2.5 times 1 and f of 3.5 times 1, right? So those are the y values. And yeah, so we can just calculate this. Of course, the function being 1 over x, we have 1 over 1.5 plus 1 over 2.5 plus 1 over 3.5. And if you type that into a calculator, you get approximately 1.352, which is actually not as good an estimation as the first one, but then we'll have another day that we'll look at why that's a better estimation more in detail, what the exact answer would be. So yeah, that's just real quick how you draw them and calculate them out. Let's do that on a few other here. So here we're gonna draw in the Riemann sum stated to approximate from 1 to 3. Notice the lower bound and upper bound goes from 1 to 3 using 2 subintervals. We're not going to actually evaluate it here. We're just going to approximate it, right? And so from 1 to 3, notice we get, if it's a right Riemann sum, we don't care about the 1. We're going to draw right here at a 2. We're going to draw our rectangle using the 2 and the 3, using the right hand of those rectangles. So let's draw the rectangles here. I think I finally broke my habit of calling these triangles. All right, phew. So real quick, is this an over or under approximation? Well, we have all this excess above, right? So this is definitely going to be an over approximation. And to zoom out and go back and compare, Remember, the right Riemann sum before was the one that was the under approximation, right? The reason, of course, here is because since this is, whoops, I want that drawn. That's strange. It won't let me erase this. The reason why the right endpoint before was the under approximation is because the function was decreasing. Now that it's increasing, the right Riemann sum is an over approximation, right? Which just makes sense there. So we have an over approximation, as we can see very quickly there. Right here, the left Riemann sum, on the other hand, is going to be using these values there and there. And so if I draw this, notice that is now going to be an under approximation, right? Because even though before the left-hand approximation was the over approximation, that's because the function was decreasing. Now that we're increasing, the left Riemann sum is the under approximation, all right? And with the midpoint, we're of course just going to find the value halfway between them. And we're going from 1 to 3, so you look at 1.5, and you look at 2.5, and you approximate those. Like so. Of course, the nice thing is it just asked us to draw the Riemann sum. Didn't ask us to actually approximate here. If we were going to approximate, we would go carry out the following and find the y values for these and multiply them. But we'll be doing that plenty in the future. So if I give you just a table, though, you need to look and see, first of all, if the table is written in equal subdivisions, because that is going to affect which of these two formulas you can use, okay? The top one will be needed if you don't have equal subdivisions, and the bottom one, whoops, it's not erasing for me. Here we go. And the bottom one will be used if you actually have equal subdivisions. So let's come on down here and check if it's equal subdivisions. Well, I see that go from 0 to 2, that's plus 2. Let's draw these. This color, here we go. Plus 2, plus 2. Each of these increased by 2, right? So because they all increase by 2, we can actually use a quick formula where we factor out the 2. Notice that matches our b minus a over n, so let's use that formula just to show you how that works. b minus a is 16 minus 0, all divided by 8, because we have 8 equal subintervals. And so, of course, that is equal to 2. And so what are we going to do? Well, we're going to use if it's a left Riemann sum, we're going to be using the first value, okay? And then the second all the way up, but we're not going to be using the last value, all right? Because that would not be the left of any of the rectangles. So what do? We have to write those down. So 10 plus 2 plus 7 plus 16 plus 2 plus 4 plus 5 plus 10. And when you add all those up, I believe it's 56. Yep. And so this whole sum, when you calculate out, you get 112. So notice we do not use the last one, okay? Because it is a left Riemann sum, all right? And that's the fast way to calculate that, okay? Moving down to the right Riemann sum, on the other hand, if we're using a right Riemann sum, now we're not going to be using the first one. So I'm going to mark a do not use here. We're going to start with the second one, and we are going to use the last one, right? So do not use this one. I do want to check and make sure it's going up by 2 each time, but it is the same table, right? So these are going up by 2 each step, so we can write down this formula. So 16 minus 0 over 8, right? And we're just going to start at 2. I'll make a little mark here. Start here. And end here, right? Now, I could write all these out. 2 plus 7 plus 16 plus dot, 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 plus all the way to 12, right? So we do that. But I also noticed before, if you think of it like this way, before I had 10 times 2 in there. This time I have 12 times 2 instead. So this number is simply going to be 4 more than the last one. You can go ahead and check that out and figure it out. But last one was 112. This one is going to be 116 because we just swapped out the endpoints, right? You could add all the stuff on the inside the same and just say, all right, take out the 10, add in the 2, that'd be 2 more. times 2 gives you 4 more. So that's where I get the 4 more than 112 or 116, okay? So a little faster way to think about that. All right, the next one, use the data given in the table to approximate using a trapezoid sum. Now, we already have the formula down, so hopefully you realize why there's the 2 in the middle and not on the ends. That's because of the nature of the trapezoid. It keeps doing this. So what we're going to do, it doesn't recognize that I make the mark. So what we're going to do, we're going to actually try to use this formula. So b minus a over 2n. So b is 16 minus a is 0 over 2 times 8, which is just 16 over 16, which is 1, right? And then we're going to add in, so we're going to add the first one plus 2 times the second plus 2 times third plus 2 times the next. And we're going to go on that way, 2 times the next one, all the way until we get near the end, 2 times 10. But then the last one, we're just going to add the 12 once, okay? Now you could type all that in there, or you could recognize, hey, on the first one, we actually used 10 2 times and didn't use 12 at all. On the first, the first time, where did the 2 times come from? Well, we multiplied by 2 because that was the width, right? On the most recent one, we used 12. We multiplied that by 2, but didn't multiply 10 at all. Here, we're going to use 12 once and 10 once. So it's kind of like an average of the two. And in fact, that is a rule that is handy to remember. The trapezoid sum is actually always the average of the left and right hand sums. Okay? And let's finish this problem, then I'll go back and show you a visual of that. So we could average 116 and 112. Halfway between those is 114. And you can go actually type that in and check that out. But it's always the average of the left and right hand sums. Why is that? Well, let's come back up here and look at our trapezoid drawing we drew right here. And let's draw in, I'm just going to use green real quick. I'm going to draw in the left hand sum and the right hand sum. Let's get a better right hand sum. There we go. So notice the space down here is the same regardless of which one you select, right? That's the same either way. This line cuts the remaining part in half. So it's going to be an average between all of this and just that part. The trapezoid is really halfway between those because it cuts the difference between them in half. And so what does that mean? That means that if you calculate the left-hand sum and the right-hand sum, the trapezoid sum is always just the average of those two sums. Okay, pretty handy. Hopefully you can see the visual proof of that right there with halfway between those two, the left and right-hand sums. So we get 114 and we're good there, right? Last one, it asks us to use a data table in the data given to approximate the same one, but this time it's a midpoint sum. And we couldn't do a midpoint sum with 8 subintervals because we don't know the values in between. So they ask us to give us only 4 equal intervals. Well, what does that look like? Well, we have 1, 2, 3, 4 intervals. So the first one goes from 0 to 4. And what's the midpoint from 0 to 4? Well, it's right here. It's 2, right? That's the midpoint right there. Midpoint from 4 to 6 would be, from 4 to 8 would be 6. The midpoint from 8 to 12 would be 10, and the midpoint from 12 to 16 would be 14. So they give us these midpoints here, and we're actually going to use those values right there, right? Let's use our formula here. So we have b minus a all over 4 because there are 4 equal subintervals. And what we're going to do then, we're going to add together just these 4 values. 1, 2, 3, 4. So it's actually a lot faster in this case. 2 plus 16 plus 4 plus 10. Now, in one sense, this is a better approximation because we're using the midpoint for Riemann sum, right? On the other hand, it's actually also a worse approximation because we only have 4 intervals. And you guys noticed yesterday, hopefully, that the more of those rectangles you have, the more accurate it's going to be. So it's kind of a trade-off on this specific example. There's no way to tell whether it's more accurate or less accurate because we're changing two things, one of which makes it more accurate, one of which makes it less accurate. Well, when you multiply all those out, you get 128. One thing I just want you to notice, 16 divided by 4, that is the width of these rectangles. It's from 0 to 4, from 6 to 10, from 4 to 8, from 8 to 12, and so on. All those have a width of 4, right? So that's just kind of double checking my work and making sure we have that down there. For number 6, we're going to use the data given in the table to approximate the Riemann sum. It's a left Riemann sum, and it only has 4 subintervals, but remember what I said to check every time. We haven't done this in a while because we've been using the same table. Always check to make sure it's written in equal subdivisions. Here, this is not, they're not even subdivisions, right? Not even. They're not equal subdivisions. So because it goes up by 3, right? It goes up by 2, then goes up by 4, then goes up by 1. So what we're going to have to do, we're going to have to calculate each of these separately, right? If this is a left Riemann sum, then the first rectangle is going to use 8, right? So we have 8 times 3, that's the width. The next one is going to use 2, that's 2 times 2 here. I got the 2 from the width. The next one is going to use 6 times the width of 4, and the last one is going to have a height of 11 and multiply by the width of 1. We can just add all those together and you get your Riemann sum. So we don't need to write that out separately. I'll just add all those together. I got 63 when I add that together, and there's our left Riemann sum. For this next one, this is a little bit trickier because it wants us to do the same thing, but this time we have to use trapezoids. And unfortunately, we can't use our handy formula. This one right here only applies, this formula only applies when the width is, when the width is even right here. Do you guys see that? So if the width is not even, we have to calculate each trapezoid by hand, okay? So fortunately, they only give us 4 that we have to do here. So let's go ahead and do that very quickly. So one thing, I have the same widths here, so that's a 3, and then a 2, and then an increase of 4, and then an increase a width of 1. And so what we need to do is we need to do 8 plus 2, the average of these first two, 8 plus 2 over 2, and multiply that by 3, the first width. Plus, then we're going to do 2 plus 6, multiply that by the next width. Then we're going to do 6 plus 11 over 2, the average of those two, times the next width. And of course, the first base added to the second base over 2, that's the generic formula, times 1. I just realized this should not be a 2, sorry, that should be a 4. So these numbers, 3, 2, 4, and 1, those are the widths of, right? I've got those right here from those widths. Okay. If it helps to draw out a picture of this, feel free to. Just sketching a little picture would probably go a long way if you're not sure where all these numbers came from. But notice these numbers repeat here. We just can't factor them and simplify them because they're being multiplied by different widths. Okay. But we can go ahead and type all that into a calculator. When you type all that in, you get 72.5. And that is that's the last problem for this day. So thank you guys for watching.